Okay, good morning, everyone. My name is Tadesse Wakjira. Today I'm going to present the work on proposed shear design equation and the reliability analysis of shear-critical reinforced concrete beams strengthened with inorganic composites. Here is a quick outline to my presentation. First I will present a quick background and overview on the subject matter. I will then talk about the research objectives followed by the proposed analytical procedure and equation. I will then discuss the results and final in-depth conclusion. To give a brief overview, a strengthening is required due to deterioration of structures, which can be caused by several factors such as corrosion or reinforcement bars, aging, and exposure of structure to severe environmental conditions such as seismic events. And advanced composites are widely used for the strengthening of deteriorated structures. And with regard to the shear strengthening, experimental evidence has shown that the use of fiber-reinforced polymer or FRPs for the shear-deficient RC beams provides substantial strength enhancement. However, they have limitations. Particularly, it has poor performance at high temperature. It greatly reduces the ductility of the structural element, and also associated with high costs due to the presence of epoxy adhesive and incompatible with the concrete substrate. As a result, inorganic matrix-based composites are developed to overcome some of the drawbacks or limitations with the use of FRP, and such composites are becoming an excellent choice for the shear strengthening of reinforced concrete beams, owing to their favorable properties such as better performance at high temperature, better substrate compatibility relative to the FRP, and improved permeability. One of the inorganic composites commonly used as strengthening system is known as fabric reinforced cementitious matrix, which is defined as composite material consisting of a sequence of one or more layers of cement-based matrix reinforced with dry fibers in the form of open single or multiple mesh as per ACI 549 guideline. The first three figures here show the most widely used fabric types in the FRCM composites, including carbon, glass, and PBO respectively. And moreover, recently, another class of inorganic composites that use steel fabrics is introduced as a cost-effective and efficient strengthening solution. So in this presentation, I will use the term FRCM to refer to all inorganic matrix-based composites for strengthening. There is a wealth of experimental research on the application of inorganic composites for shear strengthening of RC beams. However, there is limited research on assessing the shear performance of strain beams theoretically. Therefore, this research is aimed to propose a mechanical model for predicting the shear capacity of the strain beams with FRCM, develop a simple shear design equation, and finally suggest the resistance reduction factor to find the design shear capacity based on reliability analysis. So the procedure for developing the shear design equation in this work is twofold. Firstly, a mechanical model is proposed based on the simplified compression field theory to predict the shear capacity of deficient RC beam strain in shear. Secondly, the probability concept of Monte Carlo simulation is combined with multivariate linear regression to derive a shear design equation for the strain beams. So consider here an RC beam strain with FRCM within the critical shear span of A, and with dimension BW as width of the web and total height of H. The figure on the right shows the stress distribution in the critical shear span. From the equilibrium of stress for equilibrium forces in the y direction, equation 1 is valid, in which rho SY refers to the reinforcement ratio of stirrups, rho FSY refers to the yield strength of stirrups, and rho F and FF refer to the reinforcement ratio and the effective stress in FRCM, while F1 and F2 refer to the diagonal tensile and compressive stress respectively. And theta refer to the inclination of the critical shear crack from the horizontal axis of the beam. Similarly, from equilibrium force in the x direction, equation 2 is valid, in which rho Sx and Fsx refer to the longitudinal reinforcement ratio and the stress in the longitudinal bars, while the other parameters are as defined in the previous slides. From the equilibrium condition of the Monte Carlo modified compression field theory for stresses, the sum of diagonal stress and the diagonal compressive and tensile stress is equal to the shear strength times tan theta plus cot theta, where the shear strength is equal to the shear capacity divided by the effective cross-sectional area of the beam. Solving for diagonal compressive stress or F1 in equation 1 in the previous slide, and substituting into equation 3 here, the shear strength of FRCM strain beams can be given by equation 4, which can be further simplified into equation 5. In this equation 5, the first term refers to the contribution of concrete to the shear strength of the strain beams. The second term refers to denote the contribution of stirrup to the shear strength, while the last term refers to the contribution of external shear reinforcement, that's FRCM, to the shear strength of the beam. Based on the simplified compression field theory, the contribution of concrete to the shear strength can be given by equation 6, where beta is the tensile stress factor given by equation 7. And in equation 7, SXE referred to the crack spacing, epsilon X referred to the strain longitudinal tensile bar. And lastly, AG referred to the maximum aggregate size. Again, as per the simplified compression field theory, the strain in longitudinal tensile bar, that's epsilon X, can be given by equation 9. Moreover, the critical shear crack angle theta can be given by equation 10 as per simplified compression field theory. Therefore, the shear strength of reinforced concrete beams, strength with FRCM in shear, in which the fabrics are inclined at alpha to the at an angle alpha to the longitudinal axis of the beam, can be given by equation 11. And in this equation, the new variable Kf in the last term, in the third term, refer to the axial stiffness of the composites, or FRCM, which is the product of the reinforcement ratio and the elastic modulus of the composites. In equation 11, the calculation of this shear strength is not straightforward. It's an iterative process, which involves calculating or evaluating an angle theta that satisfies the equilibrium, and also determine the strain in the longitudinal tensile bar, which is epsilon X. It can be summarized in this figure. In this flow chart, the first step involves determination of the axial stiffness K for the composite, which is FRCM. In the next steps, we estimate the value of epsilon X, calculate SXE, beta and theta using equation 8, 7, and 10 respectively. Then the shear strength can be estimated from the equation 11 in the previous slide. And we calculate the value of epsilon X from equation 9. And in the next step, we compare the calculated epsilon X with the estimated value in step 2. And we make sure that it is less than the tolerance, which is taken as 10 to the power minus 8. In this study, the difference less than the tolerance. So if it is greater than the tolerance, we go back to step 2 and do the iteration. Otherwise, we go to the next step, in which we ensure that the stress in the internal shear reinforcement or stirrup is less than or equal to the yield strength of stirrup bars. And finally, we calculate the shear strength as a product of the shear capacity as a product of shear strength and effective cross-sectional area of the beam. So following the development of simplified compression field theory-based procedure for FRCM strain beams, in part of the study, this model is used to develop a simple shear design equation. So for this purpose, 5 factors were identified. 5 factors that influence the shear capacity of FRCM strain beams were identified. And in the next step, a total of 25,000 combination of the 5 factors were generated using Monte Carlo simulation. And the shear strength of each specimen was determined using the simplified compression field theory based procedure programmed in MATLAB subroutine. Actually, these 25,000 combinations represent 25,000 FRCM strain beams. And finally, a multivariate linear regression was performed using genetic algorithm to determine the relationship between the shear capacity of FRCM strain beams and its 5 predictors or factors. Finally, equation 12 and 13 are proposed to determine the shear strength of RC beam strain with inorganic composites. And these equations were primarily developed for FRCM shear strain beams, yet they can be used to calculate the shear capacity or shear strength of unstrained or pristine beams by setting the last term Kf to 0. In the first equation, we can see that the shear strength is directly proportional to the Fc prime to the power of 0.38, unlike in ACI squared, which is proportional to the square root of Fc prime. We can also see that the effect of the longitudinal reinforcement is included in the contribution of concrete to the shear strengths, concrete and longitudinal reinforcement to the shear strengths. Also, we can see that the shear strength of FRCM strain beam is almost directly proportional to the KF, is in linear proportion to the KF. Moreover, the contribution of, finally, the prediction capability of the proposed equation was validated against the experimental results of FRCM strain RC beams available in the literature, and also, which is shown in the first figure. It's also compared against available equations, code equations, which is ACI 549 guideline for FRCM strain beams. And from these two figures, we can see that, for example, R scale for the proposed is coefficient of determination for the proposed equation is 0.81 compared to 0.35 for ACI 549 guideline. And we can see the proposed equation outperformed the available ACI 549 guideline equation for FRCM strain beams. Similarly, for unstrained beams, the prediction of the proposed equation was compared with that of ACI 318, Inorganic, and Ashto equations for beams without stirrups as well as beams with stirrups. I'm here presenting as an example the first figure shows the plot of the scatter plot of experimental versus predicted shear capacity for unstrained beams without stirrups based on the proposed equation, while the second figure shows based on the plots of scatter plot of proposed, the predicted and the experimental shear capacity based on Ashto. Here is. So the result of the comparative analysis showed that the superior prediction capability of the proposed equation. This ACI 318 should be Ashto. It's superior. So to ensure now the next is reliability analysis to calibrate the resistance reduction factor for the shear capacity of FRCM strain beams based on the proposed shear equation. As we know, to ensure their safety structure designed in such a way that their capacity R is greater than the demand, which is Q here. And according to the load resistance factor LRFD, the limit state in the resistance factor format is given by equation 14. And if we consider only dead load and the life load, which is PDL and the PLL, equation 14 can be given by equation 15A and the B as per ACI 318. Here, normal distribution is assumed for both dead load and the life load based on literature review, and the parameters of distribution for dead load and the life load are given in this table based on the literature review again. And the parameters, the distribution parameter for the resistance are determined based on the collected experimental results of FRCM strain beams. Finally, the resistance reduction factor is calibrated to achieve a target reliability index of 3.5 using the least square meter in equation 16. And as we can see in this figure, the minimum LSM corresponds to a capacity reduction factor of 0.8. Therefore, a resistance reduction factor of 0.8 is suggested or recommended for a target reliability index of 3.5 for FRCM, for RC beam strain with FRCM based on the proposed design equation. Finally, the following conclusion can be drawn from the current study, from this study. Among all factors, the yield strength and the reinforcement ratio of internal shear reinforcement were found to influence the shear strength of the strain beams the most. And the shear strength provided by the FRCM system has an almost linear relationship with the FRCM axial stiffness. And moreover, the shear strength provided by the concrete is better expressed as a function of Fc prime, the power of 0.38. And the shear strength of the FRCM strain beams is directly proportional to also the longitudinal reinforcement ratio, the power of the fourth root of rho S6. And the statistical comparison of the efficiency of all the methods are the three code equations. And the proposed equation shows that the proposed equation has a significantly higher prediction capability compared to the codes of practice provision. And finally, resistance reduction factor of 0.8 is adjusted for a reality index of a target reality index of 3.5 based on the result of reality analysis. That will be end of my presentation. Thank you.
Thank you, Tadesse, for your nice presentation and keeping it within the time.